TCP puts a number in the packets. Because TCP is stream-oriented, the numbers are in fact the number of the bytes, not the number of the packets. Here is a space and time diagram. I have a machine A, a machine B. A is sending to B, and time is the vertical axis. At event 1, A has sent a packet to B. This packet has a sequence number. Here the sequence number is 8001 to 8501. Those are round numbers that in practice you are very unlikely to see. The numbers are not multiple of 100. But this is to make the diagram easier to follow. A convention that is often used in that kind of traces, in particular in Wireshark, is that the last sequence number is excluded. So that means, in fact, here, 500 bytes. So those are the numbers of the bytes in the stream that has been sent by the source. The initial number is not 0 or 1. It is a random number chosen by the source. So we start from any initial number. And then when B receives this packet, B will send some acknowledgement. There are, as we will see, two ways of acknowledging a packet. A simple way is using the acknowledgement field that is present in the TCP header. And the semantic is, if you acknowledge 8501, that means that you have received everything up to, including this number, -1. Everything. In this case, only one packet was sent. That means we have received this packet. If we would be in the middle of a connection that has been lasting for a long time, that means all the previous packets have been received by this one. This is the semantic of this ACK. Then we see 3 packets being further sent, each of them of size 500 also. 2 of them are lost. When this guy receives the third one, it will ACK this number, because that's the only thing that it can say about what has been received in sequence in the ACK field here. Now the ACK here is lost also, that can happen. An ACK is also a TCP packet. Sooner or later, A will detect that something has been lost by analyzing the ACKs that have received. A is receiving ACKs for those 3 packets, is expecting to receive ACKs from those 3 packets, and is not receiving it. So after some delay, a timeout will occur, and A will detect that those 3 things have not been correctly received, so it will resend the data, perhaps starting from here. Here it is resending this packet. And now, when B will receive this missing packet, it will send an ACK, which is for now 9,000, which corresponds to the semantic I said before. Of course, ACKing only everything in sequence is not giving all the information that the source would need. So there is a second field that was historically introduced in a second phase called the SAC, selective acknowledgement. In a case like this, B can ACK 8500, but it can also give some information that it has received some data out of sequence. This one, the third packet, 9500. So it will give a more complete information, and in TCP you can have an ACK plus up to 3 SAC blocks that allows to describe a set of received data that is not contiguous. Now, when the source receives that, it knows that everything up to this number has been received, that this third packet has been received, and probably those 2 other ones have been missing. So this guy might decide to retransmit. Here you see that it retransmits 1 packet of 1,000 bytes. A can analyze and see that those 1,000 bytes are missing. And TCP, in principle, has the freedom to organize the bytes in the packets as it wants. It's trying to optimize things. There are conflicting goals on when you should send a packet. Perhaps here the application is creating blocks of 500 bytes. So if TCP is set to be as fast as possible, there are options in TCP sockets where you can control those things. If it is set to be as fast as possible, it will always send the data when they arrive. Then if So that means the 3 packets, it will be causing 3 packets. If TCP would be less aggressive and more conservative and trying to conserve bandwidth or bit rate rather than delay, it could, when it receives one block of 500 bytes to transmit, it could wait a bit with the hope that soon there will be another block and could decide to send those 3 in one single block, for example. But most applications will, in most cases, you don't want this. However, when you retransmit, you know you have 1,000 bytes to retransmit. You can retransmit in 2, but there's no reason to create 2 packets. It's better to create only 1, because you create only 1 TCP header, 1 IP header, 1 of everything. And this is what will happen here. So you see that the sequence numbers of the packets that are received when they are transmitted or retransmitted may be different. I mean, packetization may be different. Now, when this arrives, the loss has been repaired, so the application is able to consume everything from 8,500 to 10,000. In the meantime here, if you do an application read on this socket, the only thing you can read is up to this number, 8,500. This packet, the 3rd packet of this sequence, has been received, but cannot be consumed by the application because the rule of the game of TCP is we deliver things in sequence. So this cannot be delivered. This can be delivered only once the loss has been repaired. In order to perform this, TCP uses a resequencing buffer at the destination, which is part of the socket buffer. So at the destination, packets that are received are put in a buffer. And packets that are in the buffer can be of 2 kinds. This gray shaded packet is a packet that has been received but cannot be delivered by the application. The application cannot see it because it's out of sequence. And only when the loss is repaired, the entire block will be made visible to the application here. So that's the first elements of TCP. Now, in addition to this, TCP uses what is known as the concept of a sliding window. Sliding window is a very often used concept in point-to-point protocols. Why do we have sliding window? Well, the problem, if we do just what I explained before, could be if one packet, here I call them P0, P1, P2, this is to simplify the story. Remember, with TCP, the numbering would be per bytes. But it's assuming by bad luck, a packet is repeatedly being lost. That is unlikely to happen, but on the millions of packets that a server sends, that can happen once in a while. Then what could happen if this packet is lost? Then P1, P2 are sent. They are stored in the receiving buffer. Then, of course, sooner or later, P0 will be retransmitted again. But because it's lost, the receiving buffer cannot deliver the content. So if the source continues to send in parallel to repairing the loss, which is a good idea because you want to be as useful as possible, if one is lost, there's no reason to block the source. But sooner or later, you might have a buffer overflow problem at the destination. Because if you keep sending without limits, then you will fill the buffer until you repair the loss. And the time to repair the loss might be long and uncontrolled if you have repeated bad luck. Those buffers are typically buffers inside the operating system. So they are buffers that are expensive, that take a lot of time and resources to manage. They are typically not large. We don't have megabytes of buffer here. We have more hundreds of kilobytes per TCP connection. So we're not talking of disk storage, but kernel storage here. So the solution to that, well, is simply to prevent that from happening by having a maximum number of outstanding packets. This is called the window. So the principle of the window, here I'm showing a window of size 4, which is that the size of the window is 4, and the lower edge of the window is the smallest non-acknowledged sequence number. Here I'm showing an example where we start with a window of 4, so we can send packets 0, 1, 2, 3, which we do, 0, 1, 2, 3, and say that for some reason, some acknowledgements are delayed, perhaps because there's congestion on other end here, or the network, or somewhere else. So what happens at this point here, when we are here, is that the window, when I receive acknowledgement 0, acknowledgement for the first packet, then the window moves. I can now send 1, 2, 3, 4. When I have received acknowledgement 1, I can send 2, 3, 4, 5. Now the source has sent 2, 3, 4, 5. It is shown by the fact that the window is hollow. Here the window was plain, but now it's hollow. That means we can send those, but we have sent them already. So in principle, we are blocked. So at this point, this source is blocked and cannot send anymore. Okay. The effect of this will be that on the receiving buffer size, we are sure that there can never be more than 4 packets. So if the receive socket buffer is 4, then window of 4 is appropriate here. Sooner or later, ACKs will come again. Here, when ACK number 2 comes, the window slides by 1. It becomes 3, 4, 5, 6. Packet 6 was not sent, so now we can send it. And here is an example where the source and destination are evolving at the same pace, are synchronized in some sense. Therefore, the window moves on, and 1 packet is sent at every occurrence. This is the principle of a sliding window. A little quiz now. I assume again a window of size 4,000 bytes. Every packet is 1,000 bytes. And assume we have this scenario here. At time t1, can the source send packet number 4? I close in 5 seconds. And the obvious answer is number 2, of course, if you incidentally, so we see that the destination needs a resequencing buffer, but the source also probably needs a retransmission buffer. Here, S0 has been sent, but as long as it has not been acknowledged, it needs to be, there's a chance that it can be retransmitted. So typically, operating system implementations of TCP will store the sent packets that have not been acknowledged in a retransmission buffer. When the acknowledgement comes for this, then you can safely remove them from the buffer. Now, the sliding window is necessary to make sure that the resequencing buffer is not unbounded. So we need a window of the size, the maximum, the size of the resequencing buffer. But this may not be sufficient. In practice, it's not sufficient. It would be sufficient if we can guarantee that the source and the destination work at exactly the same speed, which is in practice never possible. Here, I'm showing a source that sends packet regularly and a destination that reads 1 packet and goes to sleep or does something else and does nothing. Why would that happen? Is that a very rare case, or is that something we're likely to see in practice more than often? Any clue? Yes? Yes, the application can be slower at reading the data. You can imagine the application has a hard job to do. For example, for every packet received, it needs to go to a database. Or the application is a busy web server that is handling thousands of connections, and this is just you, so this one might be much slower. If that happens, then the data can be put into the resequencing, into the receive buffer, properly acknowledged, so everything works well. The operating system here is fast, but the application is slow. So all the data that arrive are properly acknowledged, so the sliding window will not limit the source, that will continue to send, and of course, sooner or later, we'll have the same problem as before, we'll have an issue with packet losses at the destination, which is stupid. Why send packet from a source to a destination if the destination cannot consume it? Of course, there is an obvious application to that, is that the window size should be limited not just by the physical size of the resequencing buffer, but also by how much data has been or has not been consumed by the application. And this mechanism is called flow control. So flow control is a word that in the context of computer networking means exactly this. It means you control the rate at which a source is sending in order to match the rate at which the destination can handle the data. That is called flow control. It's an end-to-end problem. It's the problem of the source being tuned to the destination speed. That is flow control. We will see that in the internet there is another thing that looks similar. It's called congestion control, which has to do with making sure that the rate at which all sources are sending is compatible with the capacity of the internet. Here is just the capacity of the destination, but there might be problems other than at the destination in the network. We might have a bottleneck link between California and Switzerland, for example, and if this link is congested, we need to slow down not just one source and one destination, but all sources and destinations. Congestion control is an entirely different topic. It's also done in TCP, but this is accidental, and we will see it a bit later. It's additional functions of TCP that in principle have nothing to do with the transport layer. They are put in the transport layer because it's convenient, but the function itself is not transport layer. Congestion control is about regulating the traffic in the network. So if we would like to be dogmatic, that would be a network layer issue. Here we don't talk about this. We talk only about flow control, which is a simpler thing. That's the thing you do if you design an application and you don't use TCP. We'll see that TCP will take care of it for you. But if you design a UDP application that streams data to a receiver, you will have to repair losses, but probably you also need to do some flow control. If your rates are variable, you have to make sure that your receiver is able to handle properly all the traffic sent by the source. So flow control in TCP is simply sent by having a dynamic window size. The size of the window is adjusted to the available space in the resequencing buffer, taking into account the packets that have been acknowledged, but that were not consumed by the application here. So here I'm showing again TCP on the left, TCP and TCP on the right. We see that when now we send an acknowledgement, in the acknowledgement we send the acknowledgement field as usual, but also the window size, which is sometimes called a credit, but in TCP is called a window. Here I'm showing it in packets. In TCP, as you can guess, it's done in bytes. So here I'm sending to A a window size of 2, which means the window is 2. 0 has been sent, so I can send 0, 1, for example. Then 0 is ACT at this point, so the window becomes 1, 2, and the window is a size 2 again, that's why it's 1, 2. Now, a bit later, the application, the B, the destination, sends an ACK for the same number with a different window size. Why is that? Well, probably because things have changed here. There is all of a sudden more space in the receive buffer. Why is there more space? There can be lots of reasons. The operating system might be fiddling with your buffer, or it might simply be that the application has consumed some data. So now there is more space, and the window has increased. If the window increases, you may, with TCP, send another ACK. Of course, what do you ACK? The same as before, 0, because nothing new has arrived, but the window now becomes 4, which changes what the source can do. Now the source can send 1, 2, 3, 4. And we can see that in the worst case here, when a full window has been received and that the window can be set to 0, this would happen in the case that we've seen in the previous slide when the destination is completely full then it will send a window equal to 0, which is the equivalent of a stop signal being sent to the source here. So when you receive such a window of 0, then you're effectively stopped, so the source gets blocked. Sooner or later, hopefully, another window field of larger will come and the source will be unblocked. Sending a window of 0 poses a number of potential problems. What if a window of 0 is sent and this ACK is lost, for example? Then we will have a deadlock situation because this one cannot send anything. This guy receives nothing, but it receives nothing perhaps because it thinks that the application on the left is not able to send because it's hanging or is late or simply has nothing to send. So the connection will be blocked, caught in a deadlock. The only difficult thing about deadlock is to detect them. Once you detect them, it's fairly easy to prevent them. Here, TCP says that whenever the window is equal to 0, you can always send at least 1 byte. So in a case like this guy would still once in a while send 1 byte of information, which might cause a little trouble on the receiving end, but the buffer is not strict and we can accommodate 1 or a few bytes. And if there was truly this packet has been lost, by sending 1 byte, it's likely that we will trigger another ACK to be sent that will have the new updated window size here. So the blocking, in fact, is not complete. We always allow, once in a while, to send a small amount of data. Here is the resequencing view of the previous slide. Here I'm showing what might have happened on the receiving side. We see that, for example, the window here had increased from 2 to 4. Then it was because there were 2 packets, the -1 and 0, that had been made available to the application, but the application did not consume it. Now the application consumes it by doing a read, and once it's read, then the light blue boxes here is the space that's available in the resequencing buffer. Now the space is 4, so we send a window of 4. So this is how TCP works, with a few more complications. The complications first are the sequence numbers are per byte, so you have more complicated things. And in a TCP association, TCP connection between A and B, in fact, there are 2 flows of information, from A to B and from B to A. So there is a sequence number space from A to B with the corresponding ACKs. So the 8,000 numbers are in the space when A is sending. But also there is a sequence space from B to A, which is here in the 100 in the lower number. So this is an example where A sends a packet to B. Now B sends an ACK, but if B has some data to send back, then it will, of course, send the data in the same packet. You don't have a separate ACK packet and a separate data packet. You can have a separate ACK packet if you have nothing to send, but if you have something to send, you will send it. So communication is very often bidirectional, even if we have the impression it is one way. For example, if you go to a web server to download something, there will be a GET here, then the GET will will cause either some redirection or some short message from the web server, or the starting of the download. So typically, there will be data in both directions. Although it's very asymmetric, if you download from a web server, most of the data is coming from the web server. So most of the ACKs from A to B, for example, would be empty. Here, the number between parentheses is the size of the packet. This is what you would see on traces like TCP dump or Wireshark. And you see here, for example, a pure ACK. This is a packet, and here, a packet of size 0, which is triggered by some change locally. Here, it is a change in the resequencing buffer that caused a change in the window advertisement. Voila, this is how TCP works. Small question about performance of TCP. plus. I close in 5 seconds. Try to close. And the correct answer is A. It's not entirely obvious, and it's true only approximately. But the intuition can be given here. If the window is large enough, you should have, and if there are no losses. If there are losses, the performance is more tricky and more difficult to estimate. We will come back to the performance when there are losses when we study congestion control. If there are no losses, we are able to, if the window is large enough, we are able to have a pipeline. That's the one way of viewing a window flow control, is that we put a pipeline on the transmission, which makes such that we can transmit enough such that when we receive the ACK, we're not blocked. If the window is small, we would have something like this. We send 1 or 2 packets, then we have to wait to receive the ACKs, and then we send again. So here, we will send less fast than the capacity of the channel. And you may remember what we saw in the first week. That's the performance of the stop-and-go protocol. Stop-and-go protocol is a sliding window with a window size of one packet. If we have a window size of 1 packet, then the bandwidth delay product becomes important because we waste some time waiting for an ACK, and we have seen a formula that captures it. If the window size is large enough, then we can avoid this problem of the performance of the stop-and-go protocol, and then the performance of TCP is exactly as large as it can be if the window can be large enough. And then the window, to be large enough, the window must contain everything that is the bandwidth delay product, which is the bit rate times the round-trip time. By the way, that was the only formula that, from the viewpoint of the units, made sense. All the other formulas in the previous slides are stupid, because this is amount of data, bits or bytes. This is time, seconds or milliseconds, and this is bits per second or bytes per second or kilobits per second, whatever, but it's data per second, time second, that gives data. All the others don't make sense. So practically, how does TCP appear to the operating system, where we use TCP with sockets? Before using TCP to send 1 byte of data, we need a bit of work, and this work is called a connection setup, shown in the next phase. Connection in computer networking means lots of things, depending on the context. Here, in this context, connection means state synchronization. There is synchronization of some state relative to the exchange of information at both ends. Essentially, the state is what is due to the window flow control. If you have a window flow control, we need somehow to initialize it. We need to know where we are, what is the highest acknowledged data that we have received, and where do the numbers start. So we need to be able to start from a correct state. Otherwise, we don't know whether we have the window should be 2, 3, the usable window, what it should be. It's impossible to find it. So that's the main reason. We have seen in the context of UDP a connected socket, which was an entirely different thing. We will see in the context of MPLS, if some of you take the research exercise, that there are also connections, also called virtual circuits or label switch paths, which is yet another different thing. But connection is always, in principle, associated with the concept of synchronization or state information that has to be in the correct, has to have the correct values before you can work with it. In order to send data with TCP, you need to do what we call open the connection. And opening is done by a synchronization packet. Here we find the fact that synchronization and connection are the same. So before sending data, you need to do those 2, perhaps 3 packets, where here we send an empty packet, which is called a SYN packet, which has a given sequence number, needs to be acknowledged. And exceptionally, when we acknowledge, although it's empty, we do as if it had 1 byte of information. That's a special rule for this one. And this acknowledgement itself needs to be acknowledged. And if any of those packets are lost, they will be retransmitted because the loss will be detected, and by the timeout, for example, or other mechanisms, and will be eventually retransmitted. It's only when this exchange is done that the end that is on the right here is in the established phase and can now receive or send data. It's only when the left end has received the second that it can send data. In practice, most applications wait until this is also sent. So the blue is the data here. If there is a connection, that means there is state information. You need to release it because this consumes operating system resources, kernel resources. So if a connection is no longer used, you need to close it, and you close it possibly on the 2 ways independently. Remember, TCP has 2 flows of information. It is possible that one flow is closing, one direction is closing, because the server has to transfer a file, and it has found end of file. So then it might decide to close the connection after finding end of file. But perhaps the other end was also transmitting something and is not finished. In particular, if some packets were lost or some ACKs were lost, it might be busy retransmitting, so both sides need to be closed separately. That gives a bit of complexity, but intellectually, it's fairly easy. TCP has its own header, like UDP, but is longer than the UDP header. Obviously, we need in TCP to have the sequence number and the ACK number and the window field. So the sequence number is 32 bits, the ACK number is 32 bit, and the window field is, in principle, 16 bits. I say in principle because there are options in TCP, and those options can include a larger window size, for example. The sequence number and the SAC block are in different places. The SAC block is in the options, which is reminding that this was invented in a second phase. And like UDP, there is the source and destination port numbers that also need to be present. The TCP ports are in the same space as UDP ports, in the same, there are 16 bits, but they are in a different space from the user viewpoint. If you send to a given TCP port and an application program is listening to the UDP port with the same number, the application program will not receive your TCP data. So a TCP socket and a UDP socket are different things. TCP socket receives data that are TCP data, which means the protocol type in IP is TCP. And even if the port number is the same, they are eventually different things. Then there is a number of other fields. Some of them are obvious, like the header length, because there are options. The header length, the header, which is in principle 20 bytes, but in many applications we have SAC, so it makes it 24 or 28 bytes. Therefore, it's variable. The SAC block itself may be variable. As I mentioned also, we can have the larger window in all of these cases that cause the header to be variable, so we indicate its length here. The reserve, as the name indicates, are not used. Then there are flags, number of flags that are bits here that I set or not, equal to 0 or 1 or no. There are 3 bits, NS, the non-speed, congestion experience, and explicit congestion notification that are used for congestion control. We will not see them now, we'll see them later. Congestion control is a function that has the goal of managing the traffic at the network layer, but is placed in TCP. So we'll talk about them later. There are the SYN bit, which is indicating whether this packet, which in principle should be empty, is a SYN packet, so a connection opening packet. And similarly, a FIN bit, which says that this is, we're terminating one side of the connection. In principle, you don't find SYN and FIN in the same packet. You can close a connection gracefully by sending a FIN, but you can also reset it by sending a reset packet. If this bit is set, that means close this connection abruptly. Don't even try to do anything intelligent about it. Probably it means that, for example, I'm sure I do that, you also do it. You go to a website, then nothing happens, and you close the window. Then the server, perhaps, is busy doing other things. Then it sees your request, responds to it, sends to your machine, but there is nobody listening on that port because the process has been killed, or the thread that was serving that port has been killed. In that case, your machine will send a reset packet to the server that will immediately abort the TCP connection. There's an ACK that is always present except in the first SYN packet, which means that the ACK field is valid. And there are things like the urgent pointer and the push bit, which in practice are not so much meaningful, but in practice they're very often set. The push bit and the urgent pointer came from old days when you were using TCP, for example, to do SSH or remote terminal from one terminal to another machine, and you're sending commands, and you, for example, you start compiling a program or a LaTeX file, and you realize there's something wrong, you want to send a Control-C, and you would like that this Control-C is handled out of sequence. Right? So remember, when TCP reads the data, in principle, it receives it and will handle it in sequence. Well, you can violate this property by using an urgent pointer. The urgent pointer will say where in the byte stream there is something like a Control-C that you should process directly. It will not change the in-sequence delivery behavior of TCP. If packets are lost, and then this will not be available. But it's an indication to the other end that is receiving, that's reading the data, the SSH application, that it should analyze the data that is at this location rather than anything else. So this is the use of it. It's a bit obsolete. I'm not sure SSH uses that kind of things today. The push bit is practically always set also. It is an indication that is given at the service interface, that means at the sender. When an application creates some data, you can decide to create it with a push bit, and if you create it with a push bit, you're giving the signal to TCP, don't delay this data, send it immediately. Because TCP might be trying to optimize, for example, if you have an application that for some reason is writing data into a TCP socket byte per byte, 1 byte at a time. Probably you don't want to do that, but in the past there were applications that were doing that. If TCP tries to be very reactive, it will create 1 packet for every byte of information, which is probably stupid. You want to wait a bit more. But if you have a good reason to do that, you mark the push bit. Today, most applications don't do byte-by-byte writing. They packetize correctly, and once they have packetized, they press the push bit to make sure TCP will not unnecessarily delay the application. This is really a service interface piece of information. There's no reason to have it in the header. It's used only at the source, but perhaps in the past there were reasons to use it. This is how we as programmers will use TCP. I'm showing here a client and a server. In UDP, a client and a server are not very different. The only difference is the client sends and the receiver receives before even sending. In TCP, it's very different. A server, by definition, is something that waits, that is up and running, and is waiting for data to arrive. A client doesn't. A client assumes that the other end is a server, therefore it can send whenever it has something to send. And a peer-to-peer application is an application that is typically both a client and a server. Here, the server, so let's talk about the client. So the client will do like with UDP, create a socket, bind it, which means bind to the, in principle, find a local port. If you're not a web server, for example, the port number will be allocated to you by the operating system. And then do a connect. Connect means connect to a remote destination. So as the arguments of the connect, you give the IP address of the destination and the port number of the destination. And the effect of connect will be to establish a TCP connection. It will be to send a SYN packet and wait until the SYN ACK is received and manage what would happen if there are losses. If things time out here, you will resend the SYN and ACK the SYN ACK here. For this to happen, you have to hope that on the other side, there is a server that is ready to receive your connect. So the thing that the server will do is create a socket and bind it. If it's a server, it will explicitly, for example, if it's a web server, bind it to port 80. And then it will do a listen. So the listen call is a different thing we have not seen with UDP. A listen call means start a queue of incoming SYN packets. And then the second new thing that we have seen is an accept. So the accept call means from the queue that has been created here, consume one SYN packet. That means create one TCP connection, which will have the effect of generating a SYN ACK and wait for this ACK to come. At this point, point 2 on the server side and point 1 on the client side, both are ready to read and write. Voilà, we'll do a break and we'll see after the break how things continue with this TCP connection.